Okay, going into our 5D notes, and we'll probably have a 5D part 2, maybe even a 5D part 3 as we get into imaginary numbers here. So this is kind of new. It's a good place to sort of introduce these things now, just because we're actually going to be using them with our quadratic functions. And so I'm going to show you how these apply here. Okay, so in previous notes, okay, um, when we do the quadratic formula again, with the quadratic formula, we have the b squared minus 4ac piece right there, which was a discriminant. Okay, now if the discriminant, okay, b squared minus 4ac under the square root thing, if it was less than zero, meaning if it was a negative number, it would have zero roots. Okay, now the function, when we graph it, will have zero roots. Okay, so we'll graph the function and it may look something like this. Okay, or it may look something like this, or it doesn't touch the x-axis at all. However, it doesn't have any real roots. Okay, it doesn't touch the x-axis, but what it has two imaginary roots. Okay, so imaginary roots means we need to have an imaginary number. So there's an imaginary number I, where I is going to be the square root of -1. Okay, I is equal to the square root of -1. All right, I'm going to show you guys how this sort of applies here, and I want to go to this problem right down here. So say we have this equation right here: 2x squared plus 11 equals -37. Okay, so we got to solve this thing by getting x by itself. So we have 2x squared plus 11 equals -37. So what we'll do is we will minus 11 to both sides. And so we'll have 2x squared equals -48. Okay. Divide by 2, divide by 2. So we'll have x squared equals -24. Okay. Doing the algebra, doing the math, we square root these things, right? So x is going to be the square root of -24. Now, can't take the square root of a negative number, but now we can. So in a way, using imaginary numbers. So instead of -24, we're going to rewrite it as -1 times 24. Okay. So x is equal to square root of -1 times 24. Knowing the rules that we know about roots, we could split those up. So x is equal to the square root of -1 times the square root of 24. Now, what's the square root of -1? Well, it's I. Okay, so x is really going to equal I times the square root of 24. Okay, so x equals I times the square root of 24. Coming back here, if I is a square root of -1, okay, if I is a square root of -1, then I squared would be -1. Okay, so I squared would be -1. I cubed would be -1i. Okay, because I cubed is really I times I times I, right? So we know I times I is -1. We still have an I there. What about I to the fourth? Think about what I to the fourth power would be equal to. Okay, and you can go ahead and try solving these two equations down here. All right, next thing. We're going to come back to the quadratic stuff a little bit later, probably on part 2 or part 3 of 5D. But I want to finish talking about I and keep it simple for right now before we move on. If we have something called a complex number, a complex number is a number that has a real part, which we'll call A, and an imaginary part, which we'll call BI. And A and B are going to be both real numbers. Okay, so a complex number might be 4 plus 2i, or 7 minus 3i, or 14 plus 6i. Those are all examples of complex numbers. We're adding or subtracting a real number with an imaginary number. Okay, and we could treat I just like any other variable. So we can rewrite, these equations. We could solve it out, combine like terms, just like anything else, and we'll have a whole number, okay, or a real number, I should say, as our A, plus or minus, then the imaginary part, which is something I. All right. Here's some more examples here that we can do involving I's. So see if we can maybe try to simplify some of these into the simplest form possible. Now, complex numbers have what we call conjugates. Now, if we have a complex number of A plus BI, the conjugate would be A minus BI. The reason we have conjugates is this is going to get more into quadratics a little bit later on. But what happens is if we were to multiply a complex number by its conjugate, you'll get a real number. So let's say hypothetically, we have a complex number 3 plus 2i. If we were to multiply that complex number by its conjugate, now its conjugate would be 3 minus 2i. If we were to multiply those two things, we would end up with a real number. We would end up with a real number. Okay, so 3 times 3 is 9. 3 times negative 2i, negative 6i. 2i times 3 is positive 6i. And then 2i times negative 2i is going to be negative 4i squared. What happens here when we multiply a complex number by its conjugate, okay, we end up with a whole real number. Here's why. The 6 i's cancel out. Okay? Remember, I squared is negative 1. Okay, so now since we have 9 minus 4i squared, really what we have is 9 minus 4 times negative 1. Which is really going to give us 9 plus 4, which is 13. Okay, so whenever we take a complex number, multiply it by the conjugate, we end up with a real number. Because these i's cancel out, we end up with a whole number, and we have an I squared number. And we could always convert I squared back to negative 1 and simplify from there. This is just going to be our background on conjugates for right now. We'll talk about conjugates a little bit more as we get into the next part of our lesson. But for now, we'll sort of leave that there. Okay. Lastly, if we're ever dividing two complex numbers, what we can do to simplify it is rewrite the equation by eliminating the complex number in the denominator. And what we're going to do is we will multiply by the conjugate in the denominator and the numerator of the fraction here. So if we were to take this quotient and rewrite it in standard form, okay, rewrite it in standard form, a plus bi, a minus bi. So we have 7 plus 5i on top and 1 minus 4i on the bottom, okay? What we want to do is we want to multiply by the conjugate of the denominator, okay? So the denominator has a conjugate of 1 is 1 minus 4i, so the conjugate is 1 plus 4i. Okay, so we're going to multiply times 1 plus 4i over 1 plus 4i, which of course is just 1. Okay, and so when we do the denominator, we have 1 minus 4i times 1 plus 4i. All right, what we're really going to end up with is 1 times 1 is 1. We have negative 4i times positive 4i is going to be, negative 16i squared. So 1 minus 16i squared being negative 1 is equal to 17. So the denominator becomes 17. On top, I'm going to do this in a different color over here so we don't get confused. So we're going to have 7 plus 5i. And we're going to times it by 1 plus 4i. All right, so we'll distribute that through. So 7 times 1 is 7. 7 times 4i is going to be 28i. 5i times 1 is 5i. Add it down here. And then 5i times 4i is going to be 20i squared. So we end up with, when we distribute this thing through here and FOIL it, 7 times 1 is 7. 7 times 4i is 28i. 5i times 1 is 5i times 1 is 5i. And then 5i times 4i is 20i squared. Okay? We can simplify this down. The imaginary part, we can simplify this down. 25i or 28i plus 5i is going to be 33i. Now simplifying the numbers down, 7 plus 20i squared, okay? Well, 20i squared is going to be negative 20 because I squared is negative 1. So 7 plus negative 20 is negative 13. So in full, if we were to rewrite this thing in standard form, we have it kind of like this. Negative 13 plus 33i over 17. And then to really put it in standard form once we're all done with it, it would really be, negative 13 over 17 plus 33/17 I. And there you have your complex number written in standard form, all cleaned up. Okay. So the conjugate's going to sort of apply here when we're dividing by these imaginary numbers, and it sort of cleans all that stuff up, particularly, down here on these last couple problems there. The rest of them, I squared is just equal to -1. Okay, so I squared is equal to -1, and so we're just going to have complex numbers down there, and that's what we're going to sort of do just for these notes right here, just to sort of get comfortable with i's before we go on to 5D Part 2, talking about um, quadratic functions that have um, imaginary roots. Okay, so that's what we have here. If you have any questions, please let me know, and y'all have a good one.